All right, so welcome to the Stoichiometry Unit in Chemistry 20. For today, what we're going to be doing is we're just going to be reviewing the different types of chemical reactions, and we're going to start off with going into a little bit more depth for formation and decomposition reactions. So, with starting off with chemical reactions, we need to understand what a chemical change is. So a chemical change occurs when two substances react to produce a different product. So if you're not creating something different, then a chemical change did not occur. Okay, so this new substance is going to be called a product. So your products are always going to be on the right-hand side of a reaction arrow, and your reactants are always going to be on the left-hand side. So the general formula for any chemical reaction, that's going to be starting with your reactants, or the things that are reacting together. And then, like I said, products are always going to be on the right-hand side of the reaction arrow. Okay, so it's important that you understand reactants are on the left-hand side of the reaction arrow and products are on the right-hand side. So there's a number of ways that we can tell that chemical change has occurred. The first of which being color change. Maybe there's some light given off from the reaction, or maybe the beaker in which your reaction is occurring gets warm, so it releases heat, or if it gets cold, then it'll be absorbing heat. Maybe a smell starts to arise, formation of a precipitate or a gas. So a precipitate is just a solid that gets produced from two aqueous solutions reacting together. Or perhaps smoke starts coming off of your solution where your reaction is taking place. So some examples of chemical reactions would be combustion. So let's say your car burning gas, would be a combustion reaction. Photosynthesis, cellular respiration, neutralization, or rusting. So a reminder, since we've already talked about neutralization in a previous unit, neutralization is just when you react an acid and a base together, and you get, if it's a strong acid and a strong base reacting together, then you'll get water and some sort of salt. So when writing chemical equations, we're trying to communicate what the reactants and products are, and a chemical equation is going to make it easier to communicate what is happening. So, for example, a solid piece of magnesium metal reacts with hydrochloric acid to produce magnesium chloride solution and hydrogen gas. Okay, so essentially what we're going to be trying to do here is we got to convert this sentence into more of a chemical equation. Okay, so solid magnesium metal. So the symbol for magnesium, that's Mg. Since it's saying it's solid, we know the state there is S for solid. And then when it says reacts with, that means that we're going to have to go plus, and our other reactant is going to be hydrochloric acid. Now, from our acids and bases unit, remember that if it begins with hydro and ends in ic acid, that means it's hydrogen with only one other element. So hydrogen, and then chlor kind of sounds like chlorine, so it's hydrogen with a chloride ion. Okay, and since acids are always aqueous, we got to write AQ here. Okay. Now it says to produce. So that means, or we can translate that word into a reaction arrow. Okay, and I'm using just a single-headed arrow instead of a double-headed arrow here, just to show or communicate that this reaction goes to completion here. So it produces magnesium chloride. So magnesium chloride. Now before I move on, magnesium, if we look at our periodic table, so let's find it. Okay, so magnesium, that's part of group 2, so it's going to have a 2+ charge on it. So I'm just writing this up here temporarily. With chlorine, since that is part of group 17, we can find it right here. Group 17 ions are going to have a -1 charge. Okay, so since 2 minus 1 does not equal 0, that's how we know we got to do crisscross applesauce. So what that means is we are just taking the numbers, not necessarily the charges, and we're just kind of placing them across like this. Okay, so I'm going to get rid of these arrows just to make this a little bit more clean, but I'm going to place a 2 behind the chloride ion, and technically I could write a 1 behind the magnesium ion. However, most of the time you can skip writing the 1, because if you're writing this with no subscript, we assume that there's only going to be one of them there. Okay, so the reason why we are doing this crisscross applesauce situation is just to make sure that this compound here is balanced. Okay. So because magnesium has a 2+ charge and we have 2 chlorides each that has -1 charge, that comes out to a -2 charge in total, which does equal 0, so this compound is balanced. Alright, now it says a magnesium chloride solution here, so that means it's aqueous. Okay, and so we can translate that to a plus sign, and hydrogen gas. Okay, so with hydrogen gas here, it's tempting just to put capital H for hydrogen and then a G for the gaseous state. However, you do need to remember that hydrogen is part of our diatomic elements. So that means whenever it's by itself, there's always 2 of them together. Okay, so an acronym that I use to help remember my diatomic elements is Hofbrinkel. So what this means is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, whenever they are by themselves, not in a compound, there are always going to be 2 of them. Okay, so that's what I use to help myself remember. Alrighty. So now we need to make sure that, like, since each compound here, or each chemical species here is balanced, now we need to make sure that the entire chemical equation is balanced. Okay, so for magnesium we have 1 going in and 1 coming out. When I say balanced, I mean we have the same amount of each element, both on the reactant and product side. So that's why I say, okay, 1 magnesium going in, 1 coming out. For hydrogen, we have 1 going in, but 2 coming out. So I'm going to place a 2 for a coefficient in front of hydrochloric acid so that we balance out the hydrogens. Okay, But that 2 coefficient doesn't just affect the hydrogens, it also affects the chlorines there. Okay, so now we have 2 chlorines and 2 hydrogens going in, and we have 2 chlorines and 2 hydrogens coming out. So that's balanced, that's all good. By the way, when you are balancing chemical equations, you need to balance using coefficients. So coefficients are just the big numbers that come out in front of the chemical compounds. Okay. Mostly where students get confused is they try and balance reactions by putting in subscripts. So this would be a subscript. However, subscripts are only used for balancing compounds. They're not used for balancing entire chemical reactions. That's the job of the coefficient. So now that we've done that as an example, let's move on to the next section here, writing balance formula equations. Okay, so a formula equation uses the word equation and substitutes the elemental symbol into it. The unbalanced formula is called the skeleton equation. So before I put in this coefficient of 2 there, we had the skeleton equation, but now that we have everything balanced with the coefficient here, this is now like a totally balanced equation. And the reason why we have to make sure that we have the same amount of each element going into the equation and coming out is because of the law of conservation of mass, which says that the mass of the reactant is going to be equal to the mass of the products. So in other words, what goes in must come out. Okay, so this is the law of conservation of mass is the reason why we have to balance the number of atoms for each element using coefficients. Okay, so you can see in this illustration here, before this reaction gets going, so the reactants are separate, we have a mass of 300.23 grams, but after they mix the reactants together here, we still have the same mass once we have the products formed. Okay, so this is just an illustration of the law of conservation of mass. All right, so let's review our Science 10 knowledge and just go over the 5 different types of chemical reactions. So for our first one here, we have 2 elements. So let's write elements above here. So element A, and then we have element B. And they come together to form a compound. Okay, so whenever you have elements coming together to form a compound, that is called a formation reaction. Sometimes it's called a synthesis reaction, but in this case I'm just going to keep on calling it formation. In the second reaction type, we're starting out with a compound, and it breaks apart into the elements that make up that compound. Okay, so reaction number 2, that's called a decomposition reaction. Okay, so formation and decomposition reactions, they're kind of like opposites of each other's. For reaction number 3, this is using a very specific example, but I'm going to make it a little bit more vague so that we can apply this template here. So in this case, we're having some sort of hydrocarbon. So a hydrocarbon is just a compound that's mostly made out of carbons and hydrogens. And we react it with oxygen or oxygen gas, which is going to give us carbon dioxide, which I'm going to put gas here. And maybe I'll change that to O2. Same thing. Okay, so we always produce carbon dioxide and water. So for this is this is called a combustion reaction, and most of the time water is going to be a water vapor. Okay, but in the case of something like photosynthesis, which is a type of combustion reaction, photosynthesis will have water as a liquid instead of water vapor, and the reason for that difference is just because in photosynthesis, the reaction conditions don't get hot enough for water to turn into a vapor. Okay? Alright, so this is called a combustion reaction. What I've written here is still pretty specific, so if I wanted to get more specific about the name, it'd be a hydrocarbon combustion reaction that I'm talking about here. But essentially, combustion reactions, you have some type of fuel reacting with oxygen, and you get usually two products, and it's the oxides of any elements in the fuels. Okay, so I'm just saying that just to make it even more generalized, but we will get into further detail on combustion reactions later. Okay, so for reaction number 4, we have a compound reacting with an element to produce some new element and some new compound. Okay. So because in this scenario, so what happened here was it looks like A and C, they kind of did a little bit of a monkey switch here. Okay, so element C reacted with compound AB and took the spot of A. Okay, so that now we have new element A and new compound CB. Okay, so only one thing is being replaced in the compound, so we're calling this single replacement. And then with the last reaction type, we have two compounds reacting together to form two new compounds. So this is going to be called double replacement. Okay. So the reason why we're going over all of this kind of generally is so that you can recognize these general reaction types to help you predict what the products could be. Because most of the time for chemical reactions, they will tell you what your reactants are, but not your products. Sometimes they do tell you your products, but not always. Okay, so that's why you need to know the general types of reactions and what they look like to help you predict the products. Okay, so we're going to dive into a bit more detail with formation here. and later we'll get into decomposition. So formation, again, that's when you have two or sometimes more elements that combine to form a compound. Okay, so in this example, I'm just going to do element A plus element B, and I'm not going to worry about a third compound, or sorry, a third element here. Okay, and we're going to get compound AB. So that's just a template for what these reactions look like. All right, for our first example here, we have zirconium metal and chlorine react together. So first off, these words react together. This tells me that zirconium metal and chlorine, these are our reactants. Okay. So for zirconium metal, I'm going to take a look at my periodic table just to figure out what its symbol is, just because zirconium isn't super common. So zirconium, that's number 40. So its symbol is Zr. And since it is a metal here, you do want to double check your periodic table just to make sure the state. So for here, we have zirconium. It is yellow, and yellow is a metallic solid. So we can say that this zirconium metal will be solid at room temperature. If the question does not specify what temperature the reaction is occurring at, you can assume that it happens at room temperature. Okay, the reason why I'm not saying, that you can assume that all metals are going to be solid at room temperature is because if we look at mercury, it's colored red or pink, whatever you want to call it, okay, which means it is a liquid. So just be careful about that. Not all metals are going to be solid at room temperature. Okay. So zirconium metal, which is a solid, and that we can translate that word into a plus sign. Chlorine. So chlorine, the symbol for that is Cl. Now for chlorine, it's part of Hofbrinkel. So that means whenever it's by itself, there is two of them. So I got to write a 2 right there. And if we look at our periodic table and look at chlorine, it is colored blue, which means that it is a gas. So I got to write that it is in the gas state. Okay, so we're just going to write a single arrow going forward. And since this is a formation reaction, we need to take these two elements and combine them into a compound. So I'm going to have zirconium chloride. Now, if we look back at zirconium here, so zirconium likes to have a 4+ charge. So I'm going to write that as a little note to myself. Chloride, since it's part of group 17, it likes to have a -1 charge. Okay, so because we know 4 minus 1 does not equal 0, we got to do crisscross applesauce. So I'm going to put the 4 right here behind the chloride ion, and I could write 1 after zirconium. However, I'm not going to, because if you write the symbol, you assume that there's already 1 of it. Okay? All right. So for zirconium chloride here, because it is an ionic compound, so ionic meaning that you have a metal and a nonmetal in the same compound, at room temperature we can assume that ionic compounds are solid, unless the question specifies that it is not a solid. Okay, so that's specifically for ionic compounds. When you have a metal and a nonmetal in the same compound, you can assume that it's solid at room temperature unless the question specifies otherwise. All right. Now, since we have zirconium chloride balanced as a compound, we got to look at the entire equation here and just make sure that the entire equation is balanced. So right now we have a skeleton equation, okay, because the entire equation isn't balanced just yet. So zirconium, we got 1 coming in, 1 going out. So that's balanced. We're good on that. For chlorine, we have 2 coming in, but 4 coming out. So those are not balanced. So now I'm going to ask myself, okay, what coefficient can I put in front of chlorine in order to make it so that we have the same amount coming out as coming in? Okay, so if I put a 2 there, now we have 2 multiplied by 2 chlorines on the reactant side. So that comes out to a total of 4 chlorines on the reactant side, and we still have 4 chlorines on the product side. So now the chlorines are balanced out. Okay, so now that that's completely balanced, we are good to go. For this next example here, let's look at it. We have chromium metal and sulfur react together. So again, this is telling you that what the sentence is talking about before, it's talking about the reactants. Okay, so chromium metal, that's number 24 here. So its symbol is Cr. So Cr, and let's just go back here. Because it is yellow, we can assume that it is a solid at room temperature. Okay, so and we can translate to a plus sign, sulfur. Now, sulfur is a little bit tricky here because not only do we have diatomic elements to worry about, we also have polyatomic elements to worry about. And our polyatomic elements are sulfur and phosphorus. So what that means for this situation is whenever sulfur is by itself, there's always 8 of them together. Okay, and if we look at our periodic table, sulfur right there, okay, is a non-metallic solid. So we can assume at room temperature it is a solid. So I'm going to write a little note underneath here as a reminder. So remember, so your diatomics, that's just Hofbrinkel. Okay, so whenever you have one of these by itself, there's always 2 of them. Okay, for polyatomic, there's only phosphorus and sulfur there. So phosphorus, when it's by itself, is P4. And sulfur, when it's by itself, is S8. Okay, so that was just a quick reminder that's separate from the question that we're dealing with right now. All right, so reaction arrow, now we got to predict our product. So since we have 2 elements reacting together, it's a formation reaction, and we need to create a compound that has both of these elements in it. Okay, so we have chromium sulfide. Now chromium, if we take a look at it on the periodic table, it is a multivalent metal, which means that it has more than one possible charge. So the question is, okay, which one do we use? Do we use 3+ or 2+? So if the question does not specify, you're always going to use the more common charge, which is going to be the first charge mentioned. Okay, so we are going to assume that chromium has a 3+ charge, and then for sulfur, let's take a look at it. So sulfur, since it's part of group 16 here, that means any ions in group 16, they're going to have a 2- charge. Okay, so that is a trend that you need to know. So 2-. All right, so since we know that 3 minus 2 does not equal 0, we got to do crisscross applesauce. So I'm going to put a 2 behind chromium and a 3 behind sulfur. So how that balances out the charges is that since we have 2 times the 3+ charge coming from chromium, that's going to give us 6+. And then for sulfur, since we have 3 times the 2 negative charge of each of those sulfurs, that's going to give us -6 or 6-, whatever you want to call it. Okay, so 6 minus 6, that is equal to 0. So that's how the crisscross applesauce situation or scenario or strategy works. Okay, now since this is a ionic compound, so we have a metal with a nonmetal, and the question didn't specify what state this product was at, we can assume that it is in a solid state. Okay, so right now we have a skeleton equation. So each of the compounds are balanced, but the overall equation is not balanced just yet. Now, technically speaking, you can start anywhere with balancing and you should get the same answer no matter where you start. Okay. However, there are certain areas or certain spots where if you start there, it's going to make your life a little bit more easier. Okay. So I'm looking at sulfur and I'm thinking that is probably going to be the trickiest thing to balance just because it's got a large subscript number. Okay, so I'm going to look at this sulfur and I'm going to think to myself, okay, what is going to be the lowest common multiple between 8 and 3? Okay, so I'm thinking in my head, okay, lowest common multiple, that's going to be 24. So 8 times what is equal to 24? 8 times 3 is equal to 24. And similarly, 3 times what is equal to 24? Well, 3 times 8 is equal to 24. Okay, so now what we have is we have 24 sulfurs coming in and we have 24 sulfurs coming out. However, that 8 coefficient here didn't just affect the amount of sulfur, it also affected the amount of chromiums. So now we have 8 times 2 chromium, so we have 16 chromium. Okay, so since there's 16 chromium coming out, we need to make sure that there's 16 chromium coming in. Okay, so by starting with sulfur, it makes it a lot easier to balance out the rest of this equation here. Okay, now just FYI, I'm just going to clean this up a little bit. So do you have to write how the balancing works out for each compound? No, you do not. Okay, I am writing that out just to show you how it is working out to help you understand, but you don't have to write that out every single time. Okay, so what I would expect in an answer would be something that I have written right here. So just the equation with everything balanced. Okay, so I'm gonna put one little reminder here. I've already talked about it, I just didn't write it down. So that's with multivalent metals, whenever you have a multivalent metal and the question does not specify which charge to use, you always use the most common charge. So a reminder that a multivalent metal is just a metal with more than one possible charge. So if the question doesn't specify which charge to use, use the most common charge. So most common charge is usually the first one. Okay. Okay, so it will be the first one listed. Okay. So I'm going to move on to decomposition reactions. So as we talked about previous, decomposition reaction is just where you have a compound that breaks apart into the elements that makes it up. Okay, so for our template example, we have compound AB breaks apart into element A and element B. I'm not going to worry about this last box. The last box would be relevant if the compound was made out of 3 different elements. Okay, so first example here, we have iron, and this should be in brackets here, iron 3 sulfide decomposed into its elements. Okay, so this is your clue that this is a decomposition reaction, the word decomposed. Okay, so iron 3 sulfide, symbol for iron is Fe. The Roman numerals 3, that refers to the charge, not how many atoms of iron you have. So 3 plus, and then sulfide, that's just a sulfur ion. And sulfur, like we said, likes to have a 2 minus charge. Okay, so we got to make sure that this compound is balanced. So I got to do crisscross applesauce because I know 3 minus 2 is not 0. So 2 and then 3. So that is now balanced. Since it is an ionic compound, because we have a metal and a non-metal together, we can assume that it is a solid because the question did not specify any other state for this compound. All right, so we have iron 3 sulfide decomposed. Okay, so that means it's a decomposition reaction, which means after my compound, I'm going to write a reaction arrow. Now, into its elements. So the elements that have made this compound up here are iron and sulfur. So iron by itself. So iron is a solid by itself. You can check that out in your periodic table. If you look up iron, it's right here. It's colored yellow. That means it's a metallic solid at room temperature. Okay, plus sulfur. Now remember, sulfur is one of our polyatomic elements. So whenever it's by itself, it is S8. And also, reminder, looking at our periodic table, because sulfur, it is, let me erase all of this, make it a little bit more clean. Sulfur is right here. Okay, so that means that since it's green, it's a non-metallic solid. All right, so right now we have the skeleton equation. Now we need to go from skeleton equation to balanced chemical equation. And once again, I'm looking at starting with sulfur. Technically, you could start anywhere, but I think my life will be a lot easier if I start with sulfur. So the lowest common multiple between 3 and 8, that's 24. So 3 times what is going to be 24? That's going to be 3 times 8 is 24. Okay. The reason why I need to use coefficients here to balance it out is because originally, here I'll just get rid of this for a second, we had 3 sulfurs going in, 8 coming out. That's why I need the coefficients, to make sure I have the same amount of each element going in and coming out. So lowest common multiple, like I said, between 3 and 8 is 24. So 3 times 8, that's 24. 8 times 3, that's 24. Okay. Moving on to iron. So remember that 8 didn't just affect sulfur, it also affected iron. So we have 16 irons right now. So we need to have 16 irons on our product side. Okay, and that's done. All right, next example. Aluminum sulfite decomposes into its elements. Okay, so aluminum sulfite. So aluminum, that's Al. Now sulfite, do not get that confused with sulfide. Sulfide is just sulfur. Sulfite, if we look at our periodic table, if it ends in ITE or ATE, it's probably a polyatomic ion. Okay, so sulfite, we can find that right here. So it's SO3 with a 2- charge there. So SO3, and it likes to have a 2- charge. And then aluminum. Aluminum likes to have a 3+ charge. Okay, so 3 minus 2, obviously that isn't equal to 0. So we got to do crisscross applesauce. However, since we would be saying, okay, we need 3 sulfites, if I just put a 3 here, that is going to change this part dramatically. Okay, which that's not what we're trying to communicate, that there's 33 oxygens. What we need to do in order to communicate that there are 3 sulfite ions is we need to put this in brackets and write a 3. So you only are going to use brackets around polyatomic ions when there's more than one. That's when you use brackets. Okay, for aluminum, we just need to write a 2 there. Okay, and now that is balanced out. All right, so since this is an ionic compound and the question doesn't specify state, we can assume that it's solid. Okay, now it says decomposes, so that means it's a decomposition reaction. We're starting with a compound, write a reaction arrow, and it breaks apart into its elements. Okay, so what are the elements that make up aluminum sulfite? Well, that's obviously aluminum. Aluminum is a metal and it is a solid at room temperature. You can double check your periodic table for that. Okay, now the other elements that make up aluminum sulfite are going to be sulfur and oxygen. Okay, so once again, sulfur, when it's by itself, is S8. Oxygen is one of our diatomic elements because it's in Hofbrinkel, so whenever it's by itself, there are 2 of them. Okay, so oxygen is a gas at room temperature and sulfur is a solid. Okay. So with balancing this, it's getting a little bit complicated because now we have 3 elements to take care of here. Okay, so sometimes it's helpful just to write a little list of everything. So I'm making a list of what I have on my reactant side, and I'm going to make the exact same list on my product side. Okay, so for the reactant side, aluminum, there's 2 of them right now in the skeleton equation. For sulfur, this 3, it applies to everything inside of the bracket, so not just the oxygen, but also the sulfur. So there's 3 times 1 sulfur here, so there's 3 sulfurs. And for oxygen, there's 3 times 3 oxygens, so that's going to be 9. Okay, and then doing the same thing over on the product side, there is 1 aluminum, 8 sulfurs, 2 oxygens. All right, so we could start anywhere. Again, because sulfur, it's S8, that's probably going to be the trickiest one to balance, so that's why I'm going to start there. So the lowest common multiple between 8 and 3, that's still 24. So I'm going 8 times 3, that's 24. 3 times 8, that's 24. Okay, so what I'm doing here, I'm still doing the same method. I'm just writing out kind of my thought process a bit more because this is a bit more of a complicated example here. So this times by 8 over here on the reactant side for the sulfurs, that's what I'm going to put as the coefficient. Okay, same with this times by 3 on the product side, that's going to be the coefficient. Okay, and like I've been saying, the coefficient doesn't just affect one element that we're talking about here, sulfur. It also affects the aluminum, the sulfur, and the oxygen. Okay, so now we kind of got to retally up what we have of each element. So sulfur is already done. For aluminum, we would have 8 times 2, 16. Okay, and oxygen's a little bit complicated here, but if I go 3 times 3 times 8, okay, which that is going to be 72. So I'm just going to cross that out, right, 72. Okay, so now we have our updated tally on the reactant side. I'm going to get rid of these arrows just to clean it up a bit. So now sulfur is taken care of, and really you could start with either aluminum or oxygen, really doesn't matter. For now, I'm just going to go with aluminum. So we have 16 aluminum coming in, we need 16 coming out. So we just updated that. So that's good now. And for oxygen, we have 72 coming in, and we need 72 coming out. So 36 times 2 gives us 72. And there you have it.